Hello and welcome everybody to Advent of Code 2023 Day 6. So this really has been the year of dramatic ups and downs after the torment of yesterday. Today is actually pretty straightforward. It's actually quite a simple problem. There's a naive solution that happens to work for both the first and the second part, and there's also a little bit more of an advanced solution that requires a tiny bit of maths knowledge that also works for both cases. So, with that said, let's jump in. This hopefully will be a quick one today. So let's have a look. Day 6. Wait for it. So as we go through our story, as is tradition, so yeah, you get the ferry that we were talking about in the last one. Now at the ferry, there's something to do with there's meant to be a big pile of sand. The pile of sand's not there. So what you have to do is you have to figure out where to get sand from. You find that there's another thing. There's a boat race. And if you win that boat race, you get an all expenses paid trip to Desert Island, which is where you figure the sand comes from. So you want to enter the boat race so that you can try and win. So you sign up for the boat race and you figure out that it's a toy boat race. So it's kind of like one of those those cars that you like pull back and let go. Except instead you hold a little button on the top of the toy boat, and depending on how long you hold it for, the boat sort of charges up, and then when you release the button, the boat will take off and keep going. And so the way you win is the boat that travels the furthest distance is the winner, obviously. So you're given a puzzle input, which is down here. And what this is a selection of different races, and for each race you're given the time of the race. So the time of each race is fixed, and you're given the record distance that's ever been traveled in that race. So those are inputs, and the goal that you have to do is you have to try and beat each of these records. So that's what we want to try and do, because if you can try and beat the record for each race, then you're pretty much guaranteed to win each race, and then you'll win first prize and get your ticket onto the boat. So we're told a few of the rules as to how this works. So when you press the button down, the timer will start for the race. The race's clock will start. So it says milliseconds in this and millimeters. The units don't matter, so I'm just gonna say seconds. So if you hold the button down for 1 second, the boat charges up by 1. So they use the units of millimeters per millisecond. I'm just going to say meters per second because it's all the same. So if you hold the button down for 1 second, the boat charges up by 1 meter per second in terms of the speed that it'll travel at. If I hold it down for 2 seconds, it'll charge up to 2 meters per second for the speed that it'll travel at. But the trick is that once I start holding the button down, the race's clock starts. So if I hold the button down for 2 seconds, 2 seconds will pass, then I let go of the button, the boat will take off at a speed of 2 meters per second, and it'll do that for 5 seconds because the overall race length was 7. I've held it down for 2, let it go, which means now the boat can travel for 5 more seconds. And that's the amount of distance it'll accumulate, traveling it for 5 seconds at 2 meters per second. So it's not terribly complicated. There's a little bit of understanding. If you've studied anything like, secondary level physics or kinematics in university or anything like that, this type of equations and problem thinking will be very common to you. If not, that's kind of my best breakdown of how to think about it. But anyway, it's not super complicated. We'll go on, we'll look at the code as well. There's like a tiny little formula that you're going to use, and that's all about that's the maths of it until the second part. We'll get to that a bit later. So yeah, I think that kind of describes the whole thing. You'll see here, they've listed out for the first race of the 7 second race, they've listed out all of the possibilities. So if you don't hold the button down at all, your boat won't move at all. So when the race ends, you'll be at 0. So that's the first case. Then if you hold the button down for 1, it'll travel a distance of 6 in that whole time. You hold it down for 2, which is the case we talked about earlier, it'll travel 10, which should make sense because we said if you hold it down for 2 seconds, it'll get to a speed of 5 meters per second. So if you let it go, it'll travel, if you hold it down for 2 seconds, it'll get to a speed of 2 meters per second. You let it go, it'll travel for 5 meters. 5 by 2 is 10, which is what our answer is here. And then so on and so forth, and go through all of them until you get to the very end, which is if you just keep holding the button down for the entire race, you won't make any distance because by the time you let it go, the race is over, so no distance will have been traveled. And that's it. So yeah, that's all the information we're given basically. And yeah, the goal is we're going to figure out how many different ways we can win the race. So how many different options of holding down the button we have to try and win the race. We're going to do that for each of these 3 races. And the answer is going to be just the product of all of those counts that we get out of it. So let's have a look at the code and see what we did. So, okay, so first thing we're doing up here, I'm just setting up some data structures to make things a little bit easier. So record all the times, record all the distances, and record all of the games. So we iterate through the file. It's only 2 lines. And we grab out the times and the distances, store them into arrays. I then just do a little loop here where I just go through them all and just store them in this hash just to make each game just an encapsulated little data point with a time, a distance, and the possible wins, which is what we're trying to count up. So then I do another loop here where I iterate through every game, and for each game I do this thing. So I basically step through this exact process for each game. So there's no need to do 0 and there's no need to do 7. So you start at 1, 2, 3, 4, 5, 6, and then you're going to count all of the things in between. The reason it's not to count those is because they will always fail, and you already know that. So we start at 1 instead of 0, and we go up to the game's max time minus 1. So for each of those times, we do this calculation. So this calculation is basically the only bit of math required for this. So this is to calculate the distance that will be traveled. The way you're going to do that is you're going to have the game time, so the max game's time, minus t. So in this case, t is how long you've held the button down for. So that will give you the amount of seconds you have remaining to travel in that round of that game. And then you multiply it by t again. And the reason you do that is because we were told that it's basically when you hold down the button, it's like a 1-to-1 relationship between how many more meters per second speed you'll get and how long you held it down for. So effectively the value t there just becomes the same thing. So you can just multiply it in by that. Then at the very end, so once we get the distance value out, so we've held down our button, it's shot off, we've calculated how far it's going to go. So now we need to determine, is that going to be a winning distance or not? So is it going to beat the record or not? So down here, all we do is we check if the D that we calculated there is greater than that winning distance. If it is, we increment the possible wins counter. That's it. So we do that for each game for the entire period that game has, all of the individual seconds that game is made up of. And then at the very end here, we just, this is just a little operation which pulls out the possible wins and multiplies them all together and gives us our answer. So this is quite fast. It runs, let's see, run it on the, so it's 6 one on the sample. And that runs, yeah, very fast. Then if we run it on our input, it'll run also quite fast. Yeah, very fast. So that's fine. That works. And that does the job and gives us the right answer. So now we come to the second part. Now, I was fairly certain for the second part they were going to do something like add acceleration to it or something like that, which wouldn't really change it a huge amount, but it would just tweak this equation really, is what it really would do. I think they've done that before. I have a distinct memory of a past problem that was like a velocity problem, and then in the second part they added an acceleration to it, but they never said that. But if you thought about it, it was effectively that they were adding acceleration to the whole thing, and you just had to code that in, which wasn't, as long as you noticed that trick, it was easy. They didn't do that here. Instead, what they've done is they've done sort of similar to yesterday, where they're taking the problem a step further by advancing the computational complexity of it, or how difficult it would be for your computer to calculate the numbers involved. So let's go and have a look and see what they've done. So for part 2, you're told that you read this input wrong, and that the line actually has very bad kerning, which is a word I've never heard before. If you look it up, it's like the offset of letters on a page. So sometimes they're like, the end of a letter matches the start of another letter. Other times they sort of overlap. So in this case, it's really bad and they're really spaced out. So what's actually the case is this is just one word. So it's one number, and this is just one number as well. So these are our actual inputs are here like this. So if you look at this, it's basically the same thing. So it's the exact same. It's just a single instance of one of these games, except you're looking at it now and the number is much, much bigger. So effectively you can use the exact same code. You just need to adjust your parsing logic slightly, and then you can use the exact same code to solve this problem. When I ran this the first time, I did this originally by doing exactly that. I just modified my parsing code, ran it, and for the sample, this value isn't that big. So I think it completed in like 0.02 seconds or something like that. So it's kind of fine. I looked at my actual input numbers and I went, that's not that big. So I just ran it on my actual input, and I think it took 6 seconds to effectively brute force the solution, and that was fine. It worked. Which is kind of what you'd expect in these early day stages problems, where very often in the early stages of advent of code, a brute force solution will work for both cases. It might be a little slow, but you can definitely sit and watch it. Previous days notwithstanding, like yesterday, for example, the brute force solution here was actually fine. But I thought I recognized immediately what they wanted us to do. And you can actually do this for both parts, but I only implemented it for the second part, which I'll show you now. So the second part now, this is where I had the reveal. If you know a little bit about maths, you will have spotted something. So in this first part, this equation should look familiar to people. And that is because it's effectively the form of a quadratic equation. So that is that if you were to expand it out and let it equal 0, it would look something like t squared minus t minus d, right, equals 0. And that is effectively, this is a quadratic equation. So all we need to do to get an analytical answer for this problem is solve that quadratic equation. So you don't need a computer to do any of this at all. You can do it with pen and paper if you want. And I'm sure if you go onto Reddit right now, there's a whole bunch of people saying that they did it with pen and paper without using a computer. So there you go. If this doesn't make a lot of sense, if you don't know a huge amount of maths, I have prepared a little sketch for you. I hope it's clear. Basically, so if you don't know what a quadratic equation is, this is what a quadratic equation looks like. So it's this sort of N-shaped equation. It can be U-shaped as well. But the real key point is it's this curved shape that crosses the x-axis on 2 points. So those 2 points are what we call the roots of the equation. And so I've got the general form written out here. It's ax squared plus bx plus c. And here underneath it, this big mess is a super well-known equation called the quadratic formula. And it's basically a generic solution for any quadratic equation that will always give you the roots of it. You just have to plug in all the values that you see there. So in our case, we plug in a is 1 in our equation, and then b and c are the time and the distance respectively. And that's it. That's all you have to do. Plug these in, get your roots, and you'll get your answer. So our 2 roots, we've got or2 and we've got or1. The 2 points were across the x-axis. The answer for R1 is we need to figure out how many values. So any value that's between those two roots is the upper part of that U of that end shape, and any of those values effectively win the game for us. So what we have to do is we have to figure out the distance between those 2 points, which again is super simple. It's just the OR2 minus OR1. That's it. That's the answer. So with that in mind, I'll show you the code to code that up. It's very, very simple. I adjust the parsing logic here a little bit just to give me a single time value and a single distance value, which I store up here. Then I feed them into this formula, which is I just need a B and a C. I know A I can ignore because it's always 1 in our equation. And then you just plug in these two equations and then subtract them to get your answer. If you're wondering what the difference between two equations, one has a plus sign and one has a minus sign. So the quadratic formula is minus b plus or minus the square root of blah, 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 blah. So that plus or minus thing, that's what gives you root 1 and root 2. So you run the equation twice, one with a plus, one with a minus, and that gives you your two roots, and that's it. So that's it. that is day 6. We can run this. I can show you. It is blisteringly fast. 6-2 on sample. That's stupid quick. And then on the input, it should be exactly the same. Basically, the runtime should be exactly the same because it's just numbers, just maths, just plugging these into the equations. The size doesn't matter. The answer will always be the same. Or the runtime will always be the same no matter what you're doing with this. So yeah, that's it. This was kind of a fun one. A little bit of a lesson in computational maths, solving problem stuff, which I know a lot of people are probably going to give out about this problem because there's a lot of people don't like this type of problem. It reminds me a lot of the type of problems you get on the website projecteuler.com, which is basically it's just all a load of programming problems that have been collected over years and years and years, but a huge amount of them are sort of numerical based ones, numerical problem solving ones, where if you know the method or you know the maths behind it, you'll get it really, really quickly. Otherwise, you'll kind of just be banging your head against it, or you'll end up with these brute force type solutions that take ages to run. I know a lot of people aren't super into those type of problems because, thinking your way around it isn't necessarily going to be the way you get a good answer. Just sort of knowing the maths is how you're going to get a good answer. So I have a feeling that'll be a complaint that's kind of leveled at this day's problem. But I'm happy because I knew the maths. So it made me feel a little bit smart when I noticed the pattern and was able to implement it quite easily. So yeah, that's it for today. But the one thing with today is, I will say, even though he's kind of put, you need to know this bit of maths, even if you don't know that bit of maths, the brute force solution is still a completely reasonable way to do it. So I feel like people will still be able to get an answer, and then the people who recognize the maths will be able to get the really fast answers. So yeah, I think it's a good balance of problems today. Certainly a better problem than yesterday anyway. So I think that's it for today. Based on what we experienced yesterday and what this literal pattern has been so far, is the odd days are terrible, the even days are easy. I'm expecting tomorrow to be an absolute hellstorm. So yeah, fingers crossed anyway that pattern breaks and tomorrow's kind of a reasonable enough one, because it's only week 1. Like, I really didn't expect these problems to be this hard. So anyway, thanks for watching, folks. I will see you guys tomorrow for day 7.